Good morning. All right, so we're going to continue our topic of graphs. This is the last topic of the major topic of the course. And now we got, so last class we just introduced it and talked about how we would represent graphs in program. Today, we're going to start looking at some actual graph problems. So here's a scenario. Suppose that you're working with some social media company. Or maybe if you don't like to think about that, suppose you built your own social media app. And one of the things that you wanted to check out was, for the sake of the advertisers, connecting with the advertisers and knowing who to target with what. Maybe you wanted to know which groups of people were connected to each other. So for example, you have, let's say you built a chat app, and so you would have all the information about who sent a message to whom. And you might say, okay, any two people who send a message to each other are somehow connected. They know each other for some reason. And maybe what you want to know is a couple of questions. You might ask, is my entire user base connected? As in, is there a way, if you're to kind of create a chain of this person knows that person and this person, or has sent a message to this person and this one to that. If you kept following that chain, would you include everybody? Or do you have islands? Do you have cliques where some people talk to each other and don't really talk to other people, and so on? How do you answer that question? How do you write code to solve that problem? And notice that you recognize that your user base might be millions of people. And if you are something like WhatsApp or Facebook, it's billions of people, or over 1 billion people. So how do you go about solving a problem like that? Let me ask you like this. Can you think of how that could be a graph problem? Okay, what would be the nodes? So when you think about a graph problem, you have to identify what are the nodes, and what does it mean for two nodes to have an edge between them, and are those edges directed? Those are the three questions you have to ask yourself. And then if there's an element of cost or efficiency in terms of, or time or anything like that, then you might also need to think about what weights should go on those edges. So let's answer those questions one at a time. What would be the nodes? The what? The people, yeah, exactly, your users, right? Accounts. Okay, what would be an edge between two? Sorry? If what? Yeah, if I've ever sent a message. Now, would you care which direction? For the purposes of the advertising, maybe not. You don't really necessarily care too much whether somebody responded. Somebody sent a message, you might presume that there's a connection there. So you might then choose if user A and has either sent or received a message to user B, then there will be an edge between their nodes. That's how you might define it. Get that? Good. Now, when you ask the question, are they all connected to each other? Can they all ultimately communicate if they were to send messages to only people they knew? Or are there islands? Are there segregated groups that don't ever communicate with people outside of that group? How do I check that question? Sorry? You want to know that spanning tree? Okay. I haven't talked about spanning trees yet, but a spanning tree might be one approach. You want to find just a path? It's kind of like what you want to do is find out all the reachable nodes from a given node, right? And so you want to then ask, are all the reachable nodes equal? Is this set of all reachable nodes equal to the set of all nodes? That would mean that your entire group is connected. Now we have a technical term for that. It's called connected. So a connected component of a graph remember that a graph is a pair of sets, V and E. So connected component of a graph G is a subset C of V, subset of nodes. Let me call it. Oh, did I mention why it's called V? Did I say it was called vertices? Okay, good. Because I often use the word node. That's just me. But the reason it's called V is because it's often called, they're sometimes called vertices as well, right? By the way, vertex, singular, vertices, plural. So nobody says vertexes, please. And nobody says vertices, okay? All right. So it's a vertex subset C such that oops, I should have said undirected. For any two nodes in C, the edge must exist.
What do you mean by undirected?
What do I mean by undirected? Did you miss Tuesday's class? So if it's undirected, it means that the pairs that form an edge is not an ordered pair. In the diagram, when we draw an undirected graph, we don't put an arrow on the edge. That's what undirected means. So the relation holds in either direction. If you're thinking formally, that each edge represents a relation, then basically the relation is a symmetric one. That's another way to, that's a COMP2211 way to put it. All right. Now, so this is what a connected component is. If it's a directed graph, then we have to talk about strongly connected components. Okay, in that case, it's the same definition, but now we have to just recognize that we have edges in both directions, so we need both to be. Wait, oh no, this is wrong. So sorry. Jesus. That was, nobody was catching me? This is so wrong. Anyway, it means that there is a path from U to V entirely in C. Now, what does it mean there to be? It doesn't mean that there's one edge, okay? It just means that you can get from U to V via possibly multiple edges. That is, what's a path? There is a sequence of nodes. Let me call them, choose a variable. Nobody's telling me. Okay, fine. Let's call them x0, which is U, x1, x2, xk, for a k length, which is V, the last one, such that for each I greater or equal to 0, xi comma xi plus 1 is an edge. Okay, so this is the formal way to write out that there is a path from U to V. There's a sequence of nodes starting at U, ending at V, in which every consecutive pair in that sequence has an edge between them. That make sense? So we'll use this notation to mean that there is this path. If I draw a little squiggly line from one node to another. So we'll say that a graph, a directed graph, if the graph is directed, we don't talk about connected components, because you could have a path in one direction. You could be able to get from U to V, but maybe you can't get back from V back to U. Yeah? So a directed graph may have a strongly connected component. Yeah. And I'm just saying, call X, U, I'm calling it X0. V, I'm calling XK. And then you have this sequence of nodes in between. By the way, in this case, the length of this, so the notion of the length of the path sometimes has a variation. We'll often use the number of nodes on the path. So in this case, it's the K+1 because I have K+1 nodes in that path. But sometimes you might see it's the number of edges, just because it kind of depends on the context. Okay? So if I use length of path and I don't clarify, I mean number of nodes, typically. But there are some occasions when, for a given problem, the length of the path is better interpreted as the number of edges on that path. And then either we'll have to clarify if it's a question you're being asked, or if it's a sub-problem, you will have to realize that, recognize that. All right, so for directed graphs, we don't talk about connected components, we talk about strongly connected components. It's a similar idea. So a subset. Let me set it up right. If G is a directed graph, that's supposed to be a V, not a U. Yeah. Say again? I don't hear the question. That's a V. So the U over there, so. And that's a V. That better? All right. So given, if G is a directed graph, let me say then. So C is a strongly connected component if for any two nodes in C, there's a path from U to V, and there's a path from V back to U. Obviously, since it's directed, the sequence of nodes from U to V may not be the same as the sequence of nodes from V back to U. Okay? Right. So let's go back to the question that we started the lecture with. How would I find, so first of all, now you know what the graph equivalent of the question I'm asking is. If I want to know, are all my users able to eventually contact each other via people they know? That's like asking, do I have a connected component, a single connected component for my graph of users, as defined earlier? If the entire graph forms a single connected component, then that graph is called connected. So a graph let's just say it like this. A graph that contains only one okay? So we'll call the graph connected if there's only one connected component in it. So the question is, how would we now discover or find out whether we have only one connected component? Or indeed, how many connected components do we have actually in all? What do you think? So here's the idea. You're going to start from a node and explore. What do I mean by explore? You're going to visit neighboring nodes. And the idea is you're going to keep visiting nodes as long as there are unvisited nodes. Meaning, as long as there's some node you haven't yet explored, you're going to go try and explore it. What does explore it mean? Just basically go there and then see what nodes it can reach. And eventually try and visit those as well. If at the end of that process, how does the process end? It ends when there are no more nodes to be explored. If at the end of that process, you have marked, so every time you explore, let's say you put a mark on that. If by the time you finish exploring, you have marked all the nodes, then you know that you have, all those are part of the same connected component. That makes sense? And so if I want to know if there's only one connected component, I could start at an arbitrary node, it doesn't matter which one, and simply explore as far as I possibly could, and then check if I had marked everything. Now, if I wanted to count the number of connected components, what I could then do is start from the first node, arbitrarily numbered, explore as far as I could. If at the end of the process I still have some nodes not yet marked, then I proceed to the first node that still don't have a mark and explore from there. And I can repeat that process until all nodes are marked. By the end of that process, I will know how many different connected components I have. So you can find out how many connected components you have by performing these explorations. The technical term for these explorations is called a traversal. Now, there are two kinds of traversals that we're going to focus on. They're not just two, they're two extremes of some decisions that you could make in between. So there's a spectrum of possible other traversals that one could make. But there are two in particular that we're going to focus on, the two extremes as I mentioned. So we can do depth first traversal or breadth first traversal. Right, so we're going to traverse for various reasons. What we do when we visit, that's really what's going to define why we're doing this traversal. So in the example I gave you, we're just trying to discover what we can reach. In that case, the traversal is what we're doing on our visit is just marking a node. Question? Let's answer that question. Question was, is it possible for the graph to be connected because you started from a particular node, but maybe if you started from a different node, it wouldn't be connected? That can't happen. Why? How would you prove that? That cannot happen. It could never happen. Because first of all, if you say connected, then you're talking about an undirected graph. And if you are connected as a single graph because you started at, let's say, some arbitrary node V0, right? So you start from V0 and you find that it's connected, but suppose you had started, you're asking, suppose I started from some other, I don't know, U, and somehow could it possibly be not connected because of that? And the answer is no, because if it's connected, I'm talking about undirected. And what we would then know is that from V0, where I started, I could reach every node, including U. Agreed? Which would then mean that if I started from U, I'd be able to reach V0. But V0 can reach everything, so therefore U can reach everything. That make sense? Now, if it were a directed graph, and it's not strongly connected, it might be possible that I start from X0, reach everywhere, but then start from U and can't reach everywhere. Because not all those edges are traversable in both directions. Okay? And that's why we reserve the word strongly connected for the directed graph. All right. So, so why we're doing the visit, or why we're doing the traversal is defined by what we do when we visit each node. And the simple example I gave you so far, we're just making a mark in it. But in practice, you might do something on that node that makes it more interesting or useful. Now, there are two, depending on the discipline of how we visit the nodes. If I write here, can you not see? All right, so then let me write here. The discipline So there are two types of traversals we're going to talk about. Depth first. And there's breadth first. But let's deal with them one at a time. So in a depth first traversal, I'm going to start from, well, again, we start from where we're told. But the rule is, you always explore from the latest node you've been at, so long as it has unexplored neighbors. So in other words, you're just going to keep, you're taking steps away from your start point, so long as each time you make a step, there's a new frontier. There's some more unexplored nodes in that neighborhood. So this is the discipline. The next node to be visited is among the neighbors, or let's see, the unexplored, that's it, among the unexplored neighbors. of the most recently visited node. Now that's actually slightly deep. So you may not fully appreciate what that really means until maybe you see an example. So suppose I have a graph that looks oops. Let me keep it undirected for now. Yes. V3 and V4. Okay, this is an example of a connected graph. Correct. The path from V3 to V4 would involve going via V1. That's how we would say that. If we said the graph is connected, that means that there's a way to get from any node to any other node. Right? We don't normally say two nodes are connected. We would say there's a path between two nodes. Or we would say the whole graph is connected, or a subgraph is connected. All right. So let's process that graph using a depth-first traversal. And now what I'm going to do is illustrate for you. I have to go back and forth. Yeah. So what you need to do? No, because you need to look at this, not me. So as I make each update, I'm going to come and mark this. I'm going to go back and write in the line. So what you can do is focus on. Let me start here, and then you can focus there, and then after I finish, you can come back and try to finish. Or if you wish, then move it as I go. All right, fine. All right, so here's that question then. Perform a depth first. So you'll often see DFS because it stands for depth first search. Okay? Starting no, it's fine. Yeah. Okay, so here's, in general, here's what we have to, we have to maintain this for any traversal. The depth first tends to be a little special in that one of these categories really doesn't matter. So in general, when you think about in general what I'm doing is traversal, we have three classes or categories that are statuses that a node could have. Those three statuses, if you imagine very beginning, I have a node that I've never seen before. So you can think of that as unseen. right? So you can have unseen status, nodes I've never seen before. Obviously, if I visited a node, then you want to give that one visited status. So those are two. There's a third status that's in between. And that is, I recognize that it's there because it's a neighbor of one that I just visited, but I haven't gotten to it yet. So it's on my agenda to go visit because I know about it, but I'm still working on something else. So that status we're going to call discovered. Okay? So 3 statuses in general, but for the DFS, the discovered status has no purpose. Reason is, we generally, I should say, no, you're going to see, all right, on my board, when I write stuff, it will have a status. If you code it, you'll see that you get away without having to explicitly represent that for free because of recursion. Okay? So, but in general, this is true. Any traversal process, in general, the nodes have 3 statuses. So there is unseen. Node has not been encountered yet during this traversal. We have visited, as I mentioned, all right, so let's run this and see how it works. So I'm going to set up a table to indicate where I've started, what has been visited, and what has been discovered so far. And then we have a discipline for how we take out the next node to choose from among those that have been discovered, right? In general, not just for depth first, but in general, we're going to start by saying, okay, wherever I start, I'm visiting. But then I'm going to explore to find out the nodes that are next to it. Those get marked discovered. And then the next node to choose to visit must be from among the discovered nodes. And that's where the discipline of how you do it, how you make that choice comes in. Right? So, so let me set up a table to illustrate the state of our nodes. So this is our DFS in G, starting from node V1. Yeah, I said that already. It's because it stands for depth first search. Yeah, and it's that's the classic. You know, when abbreviations just stick because of how they first came about, and then maybe later on scholars decide, you know, it's really a traversal because you're not necessarily searching for anything sometimes. You're actually trying to process something. So traversal is a better, more generic term. But the code and the algorithm and everything had already been created, and it was named DFS because originally it would have been searching for a thing, searching for a state. Like in a game, for example, I might be searching for a winning state. I might be searching for satisfactory, if a constraint satisfactory, I'm searching for a configuration that satisfies some constraint. So it often was categorized as a kind of search, so it made sense. But when you generalize it, you realize it's not always a search. All right? All right, so we have our visited nodes. I'm going to indicate the source from where I visited this node. And then I'm going to have my discovered nodes. And we'll soon talk about what data structure, well, probably the next lecture at this rate, what data structure I would need to maintain my discovered nodes. But let's just first get the concept straight. So I start by visiting V1. And obviously don't have any source. I didn't come from anywhere. What's my source? Which node did I come from to visit this node? That's what I'm asking. That's what source represents. So what I'm going to do is this. I'm going to mark the nodes that I've visited with an X. So it has 2 marks on it. And then as I discover nodes, meaning as I look around at my neighborhood, I'm going to put a single mark on them so you can see that they're discovered. So the process would be from your visited node, from where you currently are exploring from, mark the neighbors. And then respect the discipline according to the search. So depth first says the one you must choose next must be from among those neighbors. Now you have 3 neighbors, so let's mark them. So I now currently discover V2, V4, V3. So I would add to here V2, V3, and V4. But what I'm going to do is I'm going to add more information than that because I want to know where I came from. How did I discover them? So I'm not just going to put V2, V3, V4. I'm going to put V2, but I came from V1, like that. I discovered V3, but from V1. And I discovered V4 from V1. That's a line. If I had more space, I probably would. Oh, why not? You don't need this. Right. So at this point, we haven't said how to choose from among the discovered, as if they're all equally available, which one should you choose? So normally, if I wanted a unique answer, I would tell you that. When you code it, your code is going to presumably if it's deterministic, you didn't do something random in it, your code is always going to make some particular choice. So among the equally selectable nodes, I'll often tell you how to break ties. Okay, and so for this example, let's break ties by using the least numbered node from among those that are available. All right, and so in this case, now what I'm going to do, by the way, bear in mind, these only tie because they're all neighbors of V1. When I next explore, the neighbors of that node on the DFS have higher priority than these nodes I've just seen now. Because you must go to the most recently visited, you care about the neighbors of the most recently visited node first. So the most recently visited nodes, or sorry, discovered nodes, most recently discovered nodes have higher priority than those that were discovered long ago on the depth first. So how I'm going to do this is, since I've already written it in order like that, I'm going to use that, I'm going to make sure the higher priority elements come earlier on the left side of my list to reinforce that. Got that? So we're breaking ties by taking the lowest numbered among equally, among those that tie. And we're putting the more recently discovered nodes at the left of this sequence. So I'm going to now remove V2 from the discovered set, and I'm going to visit it. So I'm going to now mark it visited, and essentially repeat this process of exploring from V2 now. So to represent that, I'll take V2 out, and I'm marking it. So over here, conceptually, you can think of it as I just put my second line through this V2. That's why it's now visited. And I'm going to repeat this process. I'm going to explore from V2. And now V2 can see V4 and V5, right? Which means that, so we came from V1, so that's the source. Now we're going to add everything we can see to this discovered set. So in other words, we're now going to say, oh, I can see V4 from V2. All right, I'm doing this. There are two different ways I could do this. And I'm choosing one inadvertently, but it's okay. Both of these are legitimate implementations, by the way. When we know more, we'll be able to have a more sensible discussion about what ramifications of these are. At this point, do you notice that I have two instances of V4 in there? We'll talk about that later, okay? So what does that mean? That means that when I take it out to go visit, I have to actually confirm that I didn't previously visit it. That's what that means. If it's possible for me to have it in there twice, I have to make sure that when I do take it out, I check that I didn't previously visit it. All right? In a different kind of implementation, we might have to insist that this can only appear in here once. And so if I want this to have a higher priority, then I'll update this to now appear up front, and I'll change it from V4 from V1 to V4 from V2. Both will achieve the same objectives, but they require different kinds of implementations. We'll discuss that later, not today. When we finish all the traversals, we'll just come back and discuss that. Anyway, proceeding. So I noticed I put the 4 before the 5. 4 and 5 have equal priority because they're both neighbors of V2. I put the 4 before 5 because we agreed that you must use a lower number node. That's the only reason. So this means that I'm now going to take out V4. And I came from V2, so I record that. Which means that now V4 is visited. And we're examining neighbors of V4. Oh, I should have mentioned this. V2's neighbor includes V1, but I didn't put V1 in the list. Why? Already visited, so it doesn't get a discovered status, right? If it's already visited, doesn't take part any longer, we ignore it. So now when we get to V4, V4 has only two neighbors, V1 and V2, but both of them have already been visited. So that means V4 contributes nothing to the pool of discovered nodes, which therefore means that the only nodes left were in fact the what's left after taking out the V4. So that's the V5 from 2. There's 3 from 1. And this V4 from 1 is still lurking here, but it's really dead. This has no future. Because by the time, if we ever get there, it would have already been taken care of. So at this point, we remove the next one. So that's going to be 5. So notice, oops, when did 5 get visited? Oh, sorry, discovered. 5 got discovered from 2, and I forgot to put the stroke through it. And now we're just visiting it. 5 doesn't have any fresh neighbors to introduce to this. So when we visit 5, we came from 2. We're left with 3 from 1. And 4 from 1. At this point, to take out 3 from 1, we're left with 4 from 1, but nothing happens from that. When we take it out, it's already been visited. So over here, we would have visited V3 and then terminated. Now at this point when we terminate, we don't know that we've actually seen all of the graph. What we know is that we've reached everywhere that V1 could reach. So we've visited V1's connected component. If you imagine that these statuses had been a single bit that you set on a node, we would have been able to now check how many bits did I set. If it's not equal to the number of nodes, then I still have some more work to do if I'm trying to discover all the connected components. Right, so I could now represent the structure that I got in what's called a depth first traversal tree, or DFS tree, depth first search tree. And here's what it would look like. It's really just a subgraph of the original graph, but it represents the relations So I started at V1. You notice that from V1 I explored to V2. And then V2 saw V4, from V2 I got to V4 and to V5. And to get to V3 I came from V1. That's my DFS tree. You notice that all the edges in this tree come from the original graph. If you wish, I can highlight them for you. So we got to V2 from V1. So that's one edge that's in my tree. I got to V4 from V2. And I got to V5 from V2. And I got to V3 from V1. See that? Okay. Unfortunately, I'm out of time. I had hoped to do breadth first and on the same graph so you could see how they're connected or how they're related and how they're different. But that's fine. I actually was more comfortable doing depth first, being the first one, more thoroughly. In the next class, I will do breadth first. What I'll ask you to do is just remind me of that graph so I can pop up the same graph and then we can do breadth first for contrast to see how it's different. I should ask, are there any questions at this point? All right, fine. Maybe there might be, but we'll get them on Monday. Number is the leftmost we're working with because